SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 26 for aerodynamic design of axial flow compressors and fans. We are discussing about the cascade aerodynamics. In last lecture we started discussing about change of incidence angle. So we have realize what we mean by incidence angle and what all are the conditions those are bringing the change in the incidence angle. So if we recall, we were discussing about the change of my axial velocity, change of peripheral speed, and we have discussed using the performance map of single stage axial flow compressor. So we realize this change of incidence, that's what is happening with the change of axial velocity and change of peripheral speed. If I say I am decreasing my axial velocity or say I am increasing my peripheral speed, that's what will lead to give you increase of incidence angle. Now when we say increase of incidence angle, that's what is having certain change on my flow physics on suction surface of the blade. In line to that, we started discussing about what all will be the change in the CP distribution. So let's move what we have started discussing in last lecture. So here these three conditions we have discussed. We have started discussing incidence angle equal to 0. We were discussing about increase of incidence angle or what we say as positive incidence angle. We were discussing about the negative incidence angle, and if you look at this three, that's what is representing how my surface Mach number, that's what is changing along my chord. And if we try to look at and if we correlate this in sense of CP, we can say with having positive incidence angle, my Mach number distribution, that's what is giving me higher pressure rise or higher CP distribution. Then we started discussing about how we are defining as a positive incidence angle and how to define the negative incidence angle. That's what is based on how my stagnation point, that's what is located on my leading edge. If we consider the stagnation point, that's what is located towards the pressure side, that's what we are discussing or we are saying that as positive incidence angle. When we are having our stagnation point moving towards suction surface, that's what we are defining as a negative incidence angle. And here this is what we have discussed in sense of how my CP, that's what will be changing with the change of incidence angle. Now let's move ahead. So we know for subsonic aerofoils we are having different options available, but mainly for your subsonic compressor or subsonic aerofoils, what we are using, they are C4 aerofoil and NACA 65 aerofoil. Now if you compare the leading edge, then for C4 aerofoil, my leading edge, that's what is having larger radius, and if we compare that with NACA 65, for NACA 65 my radius of leading edge, that's what is smaller. Now this change or the shape of my leading edge, that's what has great impact on my CP distribution. So let's consider first NACA 65 aerofoil. So here if you look at, this is what is representing how my CP or pressure distribution, that's what is changing along the chord for particular flow angles. It says stagger angle is 33.6, camber angle is 27.3, and solidity, that's what is say 1.25, and incidence angle at initial stage it is 0, thickness distribution is 0.1, and Mach number, that is 0.6. So entry Mach number is 0.6. So both the plots, they are being done for this configuration. If we try to look at for say 0 incidence case, this is what is representing what is happening in sense of acceleration on my pressure surface, and later on how the diffusion, that's what is continue to happen on my pressure surface. If we look at here near the suction surface, I will be having great acceleration, that's what is happening on the suction surface, and that too it will be continue up to say maybe 20% of my chord, and later that's what will be giving the deceleration to my flow. So here this dotted line, if I will be putting the area under this curve, that's what is representing my pressurizing capacity of this particular aerofoil at 0 incidence angle. Now suppose if I consider say I have changed my incidence angle. Now recall, as I told, this experimentation or this data, that's what is been captured by using linear cascade tunnel. Okay, so here in this case at the entry my flow angle, that's what is being changed such that I will be having positive incidence angle. So when we are having positive incidence angle, the acceleration, that's what is happening on the pressure surface, that's what is comparatively low. And here in this case, if we consider on suction surface, I will be having higher acceleration, that's what is happening, and that's what will be giving higher pressure rise. Okay, now in line to that, if we consider for minus incidence angle, we can have our CP distribution to be lower compared to positive and 0 incidence case. Now if we look at carefully the CP distribution for C4 aerofoil, as we have discussed, this is what is having say large radius of my leading edge, or we can say the thickness of my leading edge, that's what is larger. So that's what is reflecting what is happening on my pressure surface and suction surface. So we will be having higher acceleration, that's what is happening on the suction surface. At the same time we are having higher acceleration, that's what is happening even on my pressure surface. If you compare these two, you can clearly see the difference. Now for this C4 aerofoil, as we have discussed, this is what is representing what is happening on my pressure surface and what is happening on my suction surface. Now this larger radius leading edge, that's what is giving the flexibility to blade in sense of say incidence angle. That will be comparatively less sensitive to incidence angle, and that's what is giving the priority. So most of the subsonic compressors, what we are observing, people at the initial stage, they are starting with say C4 aerofoil or British aerofoil. Many American compressors we are looking at, they are having NACA configuration, that's what is there. Now here if you look at, not only leading edge is important, at the same time this trailing edge is also equally important. So here if you look at my trailing edge for C4 aerofoil, if you look at, that's what is having certain amount of radius. Okay, so this is what is say having radius. If we compare for NACA 65, that's what is sharp edge. So many times in order to have fabrication such kind of aerofoils to make, it will be more challenging because the thickness towards the trailing edge is less. There may be possibility that it will get damaged during the manufacturing process only, and that's the reason why people they are try to use C4 kind of aerofoil at the initial iteration. Okay, now let's try to understand what all are the effect of other parameters. If we consider here, this is what is representing my CP distribution for particular kind of aerofoil. If you look at, for this case, if you look at, this is what is for say NACA 65 aerofoil, and that's what is having stagger angle is 33.6, camber angle is 27.3, solidity is 1.25, and this is what is say my design condition. Now if we look at carefully, say for my entry Mach number for say 0.2, if we consider we have used two different thickness distribution. Now remember, this is what is a thickness to chord ratio. That is nothing but the maximum thickness of my aerofoil. Okay, here if you look at my thickness to chord ratio is 0.05, that means it's a 5% thickness. Suppose if I have 100 mm chord, accordingly I will be having the thickness of say 5 mm. In line to that, this is what is we are having say thickness to chord ratio of say 0.10. So if we compare these two, this is what is giving some other kind of feeling. So if we look at for say thickness to chord ratio of 0.05, say on my pressure side you will be having less acceleration and nearly constant pressure rise. That's what we are getting on the pressure surface, and we will be having higher acceleration. That's what is happening near my say suction surface, and this is what is representing the diffusing process. So this is what is representing what is a change or what is the effect of change of thickness ratio. Okay, now say next condition, it says when we are having our entry Mach number to be 0.7. So if you compare these two, it clearly says when my entry Mach number, that's what is increasing, that's what is increasing my CP, or say for a particular aerofoil my CP distribution, that's what is changing. Now here in this case, when we are considering say Mach 0.7 on pressure surface for say thickness to chord ratio or say lower thickness of 0.05, I will be having less acceleration. That's what is happening on my pressure surface, and this is what is giving me my CP distribution. So here we need to realize one thing. Say when we are doing our design, say we are doing our design based on what all parameters we are expecting. Now from those parameters we can calculate, we can have different calculation of different parameters called say degree of reaction, diffusion factor, different angles, how they have been varying with the change of my vortex configuration. All those, that's what is giving me what will be the variation of my delta beta at the entry from hub to shroud, at the exit from hub to shroud. Now with all this data, what we need to do is this data we will be feeding for particular kind of aerofoil, because that is what is my requirement. Now at the initial stage when we are doing our design, we need to assume or we need to select one of the aerofoil for our rotor or for stator. Then after, based on what is happening on my blade surface, we need to visualize how my flow is behaving near the leading edge and how my flow, that's what is behaving on my suction surface and pressure surface. Suppose if we consider say we are having the variation, that's what is giving say positive incidence, we can say that's what will be giving may high CP distribution. If we are having negative incidence angle, that's what is giving different kind of CP distribution or say lower CP distribution. And based on our expected pressure rise at the exit, we need to play with different parameters. Now those parameters we can say one of them, that's what is the play with say variation of the thickness of my aerofoil. We need to remember when we are considering say thickness, it should not be too lower. If we consider our thickness to be too lower, it may be possible that my leading edge radius will be coming to be lower. It may be possible my trailing edge radius will be coming to be lower, because that's what is a function of thickness ratio. Let me tell you, say for leading edge, the radius roughly it is 15 to 20% of my thickness ratio, and my trailing edge, that's what I say approximately 0.5 to 0.7 of my thickness ratio. So we can understand when we are selecting this part or we are changing our thickness distribution, accordingly my leading edge shape, my trailing edge shape, that's what will be changing. It may be possible that my leading edge, that's what will be coming very thin, like as we are comparing towards say transonic kind of aerofoils or say NACA 65 kind of aerofoils. Under that configuration it will be very sensitive with the change of incidence. So it may be working fine for say design condition, but when we are moving towards off design condition it may not work fine. Okay, so it says my incidence angle, that's what is mainly been depend on my flow conditions. What flow conditions? We say what is my mass flow rate, that's what we can say, what is my axial velocity, what is my absolute velocity, what is my relative velocity. It depends on what is my rotational speed of the wheel. It also depends on Mach number, our Reynolds number. Now this Reynolds number, that's what is very important. Here we are calculating our Reynolds number based on the chord. Okay, so how my flow, that's what is behaving on my suction surface and how it is behaving on my pressure surface, that's what is basically it is giving us idea what is happening in sense of diffusion process. Okay, this incidence angle also is depend on what is my camber angle. Okay, it is depending on what is my solidity. It also depends on thickness to chord ratio. It is also depending on my leading edge geometry, mainly what is my leading edge radius, what is my trailing edge radius. Okay, now the question is, what is the use of this incidence angle? Let's discuss in a different way. Suppose say I am making or I am designing my blade. Now we know because of change of my parameters, say axial velocity, my peripheral speed, my incidence angle is going to change. So if we consider say we are having say our incidence angle when my axial velocity is decreasing, that means I will be going with the positive incidence angle. Okay, and that's what will be giving me high pressure rise. Okay, now when we are doing our design, what these designers are doing, at the initial stage only they are assuming some incidence angle. Yes, suppose if we consider near the hub, they are assuming this to be say positive incidence angle, near the tip they are assuming negative incidence angle. Now when I say positive incidence angle near the hub and negative incidence angle near the tip region, you can say with the change of my axial velocity, that's what will be working under still design condition. Just remember, suppose say I am changing my axial velocity, that's what is increasing my incidence angle. But by default we have given negative incidence angle near the tip region, so that's what will lead to work under design condition even though it is working under off design condition. We will be discussing this when we will be discussing with the design aspects. Okay, this is what is very important. Now onwards, what angles we are defining, that's what will be defined based on blade metal angle or blade manufacturing angle. So what blades we are looking at, those blades are being designed and they are being fabricated by considering the change of incidence angle. Suppose if I consider I am having my air angle, that's what is known to me, beta, that's what is say beta 1 and beta 2, mainly beta 1, that's what is known to me, I will be incorporating my incidence angle there, and based on that I will be making my blades. Okay, so this is what is very tricky. Okay, so we need to remember what is happening with the change of incidence angle. Here this is what is something different, that's what we need to realize. Here if you look at, if we are having some change in the shape of my leading edge, as I told, my incidence angle, that's what is very sensitive with the shape of my leading edge. So it's supposed to work in a normal condition like this. So this is what is my normal working condition, and this is what is my region where my diffusion, that's what is happening. Now because of some change in the geometry at the leading edge, that may be because of fabrication error, that may be because of deposition of foreign particles, that may be because of say striking of my bird or striking of say foreign object. What it will be doing, it will be modifying the shape of the leading edge, and when it is modifying the shape of my leading edge, you can say this is what is working under off design condition. Okay, so we need to be very careful for the shape of the leading edge for our compressor. Okay, now let's move towards the next understanding. Here in this case, you can understand at the entry we have discussed what we say in sense of incidence angle. Now second important parameter for us to consider, that's what we say is a deviation angle. Now this deviation angle we have discussed earlier also. What we realize, because of presence of low momentum fluid, because of growth of boundary layer, and since my blade or my aerofoil, that's what is working under adverse pressure gradient, you will be having the flow, that's what is moving away from the trailing edge, and that's what we have defined as say wake that will be coming out at the exit. And the difference of my angle, that's what we have defined as a deviation angle. Now this deviation angle, that is also equally important. Okay, so let's try to look at what we have realized. So here in this case, this is what we have discussed about say our deviation angle. This is what we have defined as a deviation angle. Suppose if I consider I am having my incidence angle to be 0, that's what is say my design condition, but still my deviation angle can never be 0. This is what is because of my inherent property of the aerofoil. This is because of what we say what is happening on my suction surface of the aerofoil. What it says, this is what is because of my flow, that's what is reluctant on the shape of my blade. Okay, so here if you look at, this is what is a region where I cannot avoid such kind of situation, and that's what it is lead to give by default this deviation angle. Okay, so deviation, that's what is prone to happen when we are talking about the aerofoil. Okay, now in order to understand what we have realized about this deviation angle, what it says, like this deviation angle, that's what is mainly been depend on different parameters. The parameters are say blade camber, we will see how that's what is changing. Okay, second, that's what is my solidity, we can say what is my chord to say pitch ratio. It is also depend on what is the shape of my camber line. Yes, this is also very important. And what will be my outlet flow angle. Okay, now here in this case, if you look at carefully, suppose if we say this is what is my deviation angle. If we look at my camber angle, suppose say this is what is my camber angle. Suppose say I will be having my camber angle to be large. So you can say this angle, it is increasing, that's what will lead to give my flow to be coming out at different angle. And since we are working under adverse pressure gradient, we have realized larger will be the turning of my blade, there are more chances for my flow to get separated on the suction surface. And that's what will lead to have thicker wake that will be coming out. That means my flow, it will be coming out at larger deviation angle. Okay, now how my blades they are being set between, say we say this is what is my pitch. Okay, so when we arrange our blade nearby, when we are arranging our blade away, that is also having the effect. Same way, what kind of camber line what we are selecting, that is also having the effect. and what outlet angle we are deciding, that also is impacting. So let's see what we say in sense. So this is what we have discussed about, say, calculation or say derivation for say deviation angle. So Carter, he has done a whole lot of experimentation, and based on those experimentation on Cascade tunnel, he has come up with the equation for the calculation of deviation angle. So reported work, that's what is older work during 50s, but as on today also, as a rough calculation, first estimation of calculation, people they are using this equation. Okay, so in NASA SP36 document, as we have cited as a reference, the details, that's what is available for different types of aerofoil, what experimentation they have done and how they have come up with the equation. So it says my deviation angle delta, that's what is equal to m into theta square root of s by c. So as we have discussed, my deviation angle, that's what is mainly been depending on what is my camber angle and what is my say s by c ratio. It says this m parameter, that is very important. This is nothing but it's an aerofoil parameter. Just look at, this is what is say my aerofoil. If I am looking at, this is what is the location where I will be having my thickness to be maximum. This is what is representing say maximum camber location. I say that point as a point A. So this is what is say my point A. Okay, and this is what is in reference to chord. So here we have written that as L because I am using this nomenclature. Basically this is nothing but this is what is my chord. Okay, so what it says, my m, that is equal to 0.23 into 2a by c square plus 0.1 alpha 2 by 50. Suppose say if I am considering this equation for say rotor blade, in place of alpha 2 we will be having beta 2. Okay, and as we have discussed, A is a distance of the point of maximum camber. So this is what is a location of maximum camber from the leading edge. Okay, this m, that's what is varying with different kinds of camber lines what we are selecting. We will see what exactly is the meaning of different kinds of aerofoil very soon. It says when we are having say circular arc camber line, my 2a by c, that's what is equal to 1, and we know like deviation angle, it is inherent property for say our aerofoil. So same logic that can be applicable for our inlet guide vane also. So what it says for inlet guide vanes, this deviation angle, that's what is given by 0.19 theta s by c. Okay, so this is what will give us idea about how our deviation angle, that's what is changing with. Now as we have discussed, we are moving towards very aggressive designs. When I say very aggressive design, the meaning is we are moving towards say high pressure rise to be expected from our blades. When we say we are expecting high pressure rise, it is bound to happen, my delta beta, that's what is going to be high. Okay, and under that condition we need to do careful calculation for this deviation angle. So based on older available data from the Cascade tunnel, people they are taking this deviation angle as a first cut approximation. Now with availability of our computational tools, people they are realizing what is happening near the trailing edge, and based on the flow visualization, based on CP distribution, based on detailed flow field study, people they are modifying this deviation angle and just try to make the flow to be in line to what we are expecting. Okay, so the use of this computational tool, that's what is helping us in sense of deciding this deviation angle. Now what we are talking about this deviation angle calculation using say computational tool, that's what is depending on what kind of say turbulence model we are selecting with. Okay, we will be discussing what all are the effect of change of Reynolds number, because that's what is very important in sense of calculation of this deviation angle. So we can say today we have discussed about how do we move with the change in say incidence angle, what all are the parameters which affect the incidence angle, and we have realized by mass flow rate, speed, Mach number, Reynolds number, they are the flow parameter we are changing the incidence angle. At the same time, we are having our blade geometry, we are having our thickness distribution, the shape of the leading edge, shape of the trailing edge, the radius of the leading edge, all those say blade parameter or the cascade parameters, or we say aerofoil parameter, that's what is changing the incidence angle. And we have started discussing about with the change of incidence angle, at the exit we will be having the change in the deviation angle. And we learn deviation angle, that's what is prone to happen because of the inherent property of our aerofoil, and we need to be very careful in sense of calculating this deviation angle. Okay, so with this we are stopping with. See you in the next lecture. Thank you very much.